Now I want to talk about bias-variance trade-off. Now, bias-variance trade-off is something very, very important to machine learning, and it has to do also with the splitting of data in train and test data, which you might have seen around already, and it is something really which needs to be done for any machine learning technique, and it's something quite different maybe to the traditional thinking if you look at, say, linear regression in a statistics course. So I will try to explain it carefully so that you get a good grasp of this concept and will be able to apply it throughout the course, as this is something very important indeed. So rather than looking at a real life example, I think it's easier to look at again a kind of toy example of simulated data. It might look a little bit contrived to those who know the concept already, but I think it helps to look at something very simple first and understand the concept, and then we can look at real data examples in the tutorials, and you will see how it actually looks like then. But it can be a bit more trickier to see it in real data examples. So let's just look at this very simple toy example first. So let's here look at a true model. So we have a true relationship which is quadratic. So the equation is given here. This equation is just the dashed line which you can see in the figure there. So the dashed line is a true relationship, and I'm now observing a number of data points, in this case 10 data points, which are coming from the true model plus some noise here, which is given by this Gaussian distribution with variance 1. So here, the first observation, the noise was very small, it's nearly on the line. Second one as well. Third observation here, have a bit of more noise, for example. This red line is just nothing else than the epsilon for this observation. So very similar to the linear regression example, just having a quadratic curve. The question is, what will happen if I now fitted functions of different polynomials to it? I could fit a linear function to it, I could fit a quadratic function to it, I could fit a fifth order polynomial, 10th order polynomial, I could fit various polynomials to it. And that's a question we often face in machine learning, like in neural networks, for example. The bigger the neural networks, the more nonlinear it becomes. So where do I stop? What is the best model for this type of data, and how can I know it if I don't know the true relationships, the dashed line, which now we obviously see, but what if I do not know the dashed relationship? How can I somehow see just from the data I have whether what I did was something good or not? So let's just look at this specific case. What happens if we fit several polynomials, as I just mentioned, one of first degree, second degree, fifth order, and 10th order here. You can see the first order is the red line, is a linear model, so this will fit the data points okay, but it's still quite far off to the true model, which is the dashed line. Now the green line is the quadratic model, which unsurprisingly fits the dashed line the best, just by looking at it with the eye, without any kind of resorting to any more fancy measures. The fifth order polynomial still looks okay. It's quite close to the green line. It's mainly once I start going out at the edges here, it will probably, oh, what did I do now? At the edges here, it will probably start deviating more, but actually within the kind of central region of the data, I observed the fifth order polynomial, which is the bluish line, also observes quite, also looks quite well. Now the 10th order polynomial actually fits the data perfectly. You see, it goes through every single of the black dots. So if you looked at the least squares error, is actually 0 in this case, and you might want to pause for a second and actually convince yourself that once you go down from polynomial of degree 1, 2, 3, 4, 5, once you include more terms, the error on this data can actually only go down. So just pause for a second and think about it. Hopefully it will be clear why this is the case. It has to do with the optimization problem, because effectively the optimization problem for the fifth order polynomial is exactly the same as that for the second order polynomial if I choose the other coefficients equal to 0. So it's a subcase, so I can always obtain the solution from the second order polynomial if I take the fifth order and just set some to 0. So I must do at least as good. This is why the error can only go down. And in this case, once I have as many parameters as data points, I can solve the problem exactly, and I get this exact matching fit, which goes to every single point. So that sounds nice, but kind of, I think you already know where this is going. This kind of violet line, the 10th order polynomial, isn't really such a good fit. So why that's the case, maybe it might not be that clear when just looking at this picture, but if I think if this data is kind of some small sample from a population of points, and if I want to have a model which applies to all of the population or to new data, then obviously this 10th order polynomial might not be at all a good fit, because it could be that now I sample a new point, and this new point could be here, so a new point for the observation could just be here at the bottom, and this point is obviously quite far off from the violet line and much closer to the other lines there. So here you see that actually if I were to look at new data, then I would get a rather bad outcome from looking this last model. In a sense, a more robust model would be the green line or the violet line, because they also perform well on new data. And this is really this issue. So what happens if I got new data? How well would my model perform? It doesn't really help that it's performing well on this small sample of data which I have. It should be working well in general, and this is where sometimes people say I'm overfitting, I'm fitting to the data, because the violet line in a sense is just fitting to the noise in the data. It replicates exactly the noise, but obviously the noise will be different if I get new data samples, so that won't be very helpful. And this is the basic idea behind the biased variance trade-off, but the question is, how can you calculate it? So this is just what I just said in words. So we have kind of higher flexible models like the 10th order polynomial. They are a perfect fit to the data. The least squares error goes to 0, but kind of by the eye we already know it's not a good fit in terms of its capability of generalizing to new data. But the question is, how can we capture it? And in practice, what I can do, I can just get a new data set, say the test data, could have been some genuine new data, and or some data which I didn't look at before, and I can just evaluate it and see actually how for new data does it perform. Exactly as I did with this 1 point, I could instead get myself 10 new points and say, okay, how does this model actually perform on those 10 new points? And I will see that the green line, for example, does perform quite similarly on new data as well as on the existing data, whereas the violet one varies quite a lot. In this case, it gives a perfect fit, but in the case of the new point here, it gives a terrible fit. So it's a lot of variability, and this is what I sometimes called high variance. And in general, we have this relationship here, which is what is sometimes called the bias variance trade-off. So I have the root mean squared error. So this is kind of my error on the test set. It's effectively just the least squares error, but the square root of it. So I have this error, and I'm looking at it on a test set. So I have a genuine new data set. I'm looking, how does the error vary if I vary the flexibility? So here I have models with low flexibility, and here I have models with high flexibility. Low flexibility could be, say, the linear model, and high flexibility in our case could have been the 10th order polynomial, for example. This is very high flexibility. It can give me a very wiggly line. The linear model is very rigid. It just gives me a linear relationship. So what happens, we already saw that the training error, so the error on the data set where I fitted the model on, which is this one here, is always going down. And hopefully you convince yourself that mathematically speaking, the more parameter I include, it can only go down necessarily. And once I give it enough parameters, like in this case, if I have as many parameters as I have observations, I can fit the data perfectly, and this line will kind of eventually go down to 0 here. On the other hand, the test error can go up again, which is what I see here. So the test error actually for the linear model is high because the linear model was a bad approximation to my quadratic line. For the quadratic model, the error was quite wide, but then for the 10th order model, I could see that actually for the 10th order model, if I get new data, it didn't look at all so good, and the error was actually going up again. So in general, I will have this relationship. If I have very low flexible model, the test error will be high. Then I increase flexibilities up to this sweet spot where I have kind of the minimum test error. But then if I make the model more and more flexible, I will start fitting to the data. So in this regime here, I'm kind of what is known as overfitting. And this regime here, I am underfitting the data. In this case, my model is not flexible enough. I can't capture the relationship. The relationship truly is quadratic, and I'm only giving it a linear model, so I can never do as well as if I had a quadratic model. However, if I give it a 10th order model, then I'm just having too many parameters. It's just too easy to fit to the noise in the data, and I'm just overfitting. So I'm getting a worse model. Not a worse model on the training data, but once I start looking at new data, my error goes up again. And I can actually see that this error, let me maybe get rid of this over and under fitting, it's getting a bit cluttered here. So this test error is nothing else than a combination of the variance and the bias term. And this is what is called the bias variance trade-off. It's effectively this relationship here. The test set error is just equal to the variance plus the bias there, and those are plus the irreducible error, which is just the noise in the data. I can never bring it to 0 if there's a lot of noise in the data. So let's just see what this means. So bias, which is the yellow term, goes down if I have a more flexible model. Bias, effectively, you can think of it, bias is the how well would I do if I had an infinite amount of data. For example, in this case here, for the linear model, even if I had an infinite amount of data, I will never get a perfect fit to the quadratic line because my model is just not flexible enough to fit to this curved shape. I can only do straight line. So I will still have a difference there, even if I had an infinite amount of data. This is called bias. But once I go to the quadratic model, I'm already getting a good fit, and once I had infinite amount of data, I would get a perfect fit. The same is true for the 5th order as well as for the 10th order. It obviously now doesn't look so well, but if I had an infinite amount of data, I would get a perfect fit as well for the 10th order model. So in this case, the bias, which is this difference once I get to the infinite data limit, is kind of positive for the 1st degree, and then basically goes to 0 for the 2nd and 5th and 10th order polynomial. And in general, it will be some decreasing function like the yellow line. The more flexible I make the model, the lower this term becomes. And in principle, once I go to very, very flexible models, I can effectively get this bias down to 0. If I had some gigantic neural networks with millions of parameters, I can get this bias down to 0 because I can fit about anything. And in fact, you can prove that any continuous function can be approximated by a neural network with an infinite amount of neurons. So I can actually go down to 0 with the bias term. but then another term is kicking in, and this is this variance term. So this is the first one we discussed is the bias term, and the second one here is this variance term. And the variance is exactly what I mentioned earlier. How would my error change if I had some new data here? And we saw that in this example, for the quadratic model, even if I sampled new data, I will roughly get the same fit. Whereas for the 10th order one, if I had new data, my fit might look quite different. So maybe I get some new data like this one here, this one here, this one here. Now my new fit will look like this. It will look completely different to what I've seen already. And this is why I say there's a lot of variance in the model. And this variance goes up. So the more flexible I make the model, the more likely that I incur this variance here. And in general, I have bias going down, variance going up, and the test error, which is effectively just the sum of the two, plus the irreducible error, will have this nice shape here, this U-form shape, which you see here, where I have too high of an error if I have the model not flexible enough, and then just the minimum error if I have just the right amount of flexibility, and then the error goes back up again if I make the model too flexible and I start overfitting. So again, this region here is called overfitting, this is called underfitting, and this is just right here in the middle. And really, in all of our machine learning tasks, it's about playing with the different models, playing with the flexibility, varying across this line here, and finding out where is the sweet spot, where do I have the best trade-off between bias and variance, such that the combination of the two is minimal there. And in practice, to do so, I will have to leave out some test data set. So what I do is I don't wait for new data to come in, but I take my existing data and split it, and we will talk more about it in the exercises, how to do it. I could just randomly split the data. A typical split would be, say, 2/3 of the data randomly are assigned to the training set, and 1/3 of the data is assigned to a test set. And then basically I fit my model to the training data, which could be a linear regression, and it will just be fitted using this data set here. Then I obtain my optimal model, and then I can evaluate it on the test data and say, if I wanted to look at the previous example, I could now fit the linear model evaluate as a test data, fit the quadratic model evaluate on the test data, and so on. And I can effectively reproduce this red curve here. I can fit the linear model, evaluate it, fits the quadratic model evaluated, fits the 5th order model evaluated, fits the 10th order evaluated, and I will see actually the error was minimal here when I had the quadratic model. So I would know that the best model to take is the quadratic model. And this is a very generic framework here. Rather than looking at some statistical error such as R squared, what I'm really after is the error on the test data set, and which is supposed to be a new data set which hasn't been seen by the training procedure. And this is something which often you can get wrong. You might somehow maybe do some computations before you do the splitting, and then by mistake you've kind of messed up everything, and your model has a chance to see already the test data. So you have to be very careful when you do the splitting, and again we will talk more about it in the tutorial, but the basic idea is I have some training data and I have some test data, and I must make sure by evaluating different models which I trained or fitted on the training data, by evaluating them on the test data set, I must make sure that I'm neither underfitting nor overfitting, and I want to have some form of varying the flexibility. In this case, varying the flexibility means increasing the number of terms in the polynomial model, but we will see later that when we do regularization on day 3, there are better ways of varying flexibility. I can introduce some continuous parameters which help me to effectively vary this flexibility on a continuous scale. So hopefully this gives you some rough idea on how this idea of bias variance trade-off works, what are train and test data, and how it is actually used in machine learning. And this is something very generic. We haven't really said that this has to be applied to linear regression or to polynomial regression. It can really apply to anything. Any model which we look at, being it the simple model this week or the more complex model next week, will be based on this principle there. I always have to look at the data, split it up in some training and test data, and we will find and look at more fancy ways of doing it than that, but I will have some way of splitting the data, and then I fit the model or train the model, that's why it's called training data set, on the training data, and then I will evaluate it on the test data, making sure that I find the model with the best test error, which is neither underfitting nor overfitting there, and then I'm making the best trade-off between bias and variance in my model.